Hi, I'm Michael, and I'd like to introduce you to Saber, an innovative solution addressing Australia's need to update its recycling industry. Saber in Spanish means knowledge. I called it this because its main goal is to disseminate important information that aims to bring Australia to the cutting edge of plastics recycling, providing an educational experience for the public and a unique marketing opportunity for this company. Before I go into more detail though, allow me to explain why this product represents such an important milestone for Australia's transition into a circular economy. Since we started producing plastic in massive commercial quantities back in the 1950s, more than 8 billion tonnes has been produced. That's a fairly incomprehensible number, but if you average that out, that is equivalent to producing about as much plastic as an adult rhino weighs, or 400 slabs of beer if that's easy to imagine. That much plastic every single second for the last 70 years, non-stop. This in and of itself isn't bad. What makes it bad is that less than 10% of it has ever been recycled. And of that, only a small fraction is still in use today. And the rest, well, it's everywhere you don't want it to be. In the ocean, polluting rivers, coastlines, and buried in landfills, taking with it all the value that we once placed on it. Plastic pollution sucks. It's an eyesore, it's bad for our health, and economically it's a disaster. Mechanical recycling is the process that Australia's recycling infrastructure is capable of now. Because of our commingled recycling setup that collects all types of plastic together with paper and metal, it's energy intensive and difficult to sort, which puts extra strain on recycling plastics because even the tiniest amounts of contamination can make the process impossible, leading to large volumes of Australia's recyclables ending up in landfill. Conversely, chemical recycling encompasses any process that essentially reverses the steps taken during manufacturing. We define plastics as a subset of a broader group called polymers. Polymers are just large molecules made by joining a bunch of smaller molecules called monomers together in long chains. Chemical recycling breaks down these chains back into the smaller monomer pieces that made them, simply called depolymerization. This process outputs raw material that can be used to manufacture virgin plastics. In order to rip these long chain molecules apart, you need heat, pressure, and catalysts, or some mix of the three. My industry partner Pyrowave is a Canadian company that achieved this with polystyrene. They use microwaves to create the necessary heat. This is the cutting edge technology that sparked the idea which ended up as my final product. Saber, an educational exhibition installation that also acts as a fully operational miniaturized chemical recycling plant. As a complete unit, it contains a plastic shredder, a small extruder, and a high-powered industrial microwave setup that is capable of recycling about 100 kilos of plastic a day. This machinery has been chosen for the purpose of public demonstration and material output. The shredder and the extruder exemplify the mechanical recycling process and aid in the explanation of the technical differences between the mechanical and chemical. They also prepare the material for the microwave oven by increasing its density, allowing more material to fit in. The plastic proposed as the initial commodity of choice is polystyrene. This is because in its monomer state, it is a liquid at room temperature, making it much easier to work with. The microwave oven works by blasting high power microwave energy into the main chamber, which will be absorbed by the plastic, heating it up beyond its melting temperature and up to a point where the polymer chains can no longer remain intact. The chains will break apart into tiny pieces, those monomers from before, which will be in a gas form at this high temperature, rising through the condenser column at the top to be cooled and then collected as a liquid from the collection tank below. Zooming out, the structure that all of this technology resides within is the focal point of the design for this product. It is a fully modular unit consisting primarily of a steel frame, hardwood columns, and aerated concrete panels. The modularity of this structure is a key feature that allows for easy disassembly. This is hugely important for the exhibition aspect of it, as exhibition venues generally only allow a 12 to 15 hour window for installations to bump in and bump out. To accommodate for this, I've designed it to be assembled in around 10 hours by a team of 4, although a small forklift is required to lift the heavier components into place, the heaviest of which weighing around 140 kilos. To make transporting the system between venues as simple as possible, all of the components, including the recycling equipment, can pack down and be stacked into a standard 40-foot shipping container, which can then be loaded onto a truck for transport. And at a total weight of just under 9 tonnes, it sits comfortably below the weight limit for this size container. The steel frame provides the structural strength required to support all of the other components. Each member is hot rolled, cut, drilled, and welded to suit a specific place within the frame. The lengths that curve around the corners also require roll bending to achieve their desired radius. Once fully prepped, all steel members are also powder coated to improve the surface quality and overall appearance. Extensive FEA testing was undertaken on the most structurally vulnerable members that it was calculated would experience the highest loading, these being the lintel spanning the front entrance and the curved floor members in the rear. Many iterations for the cross-section of the entrance lintel were tested, resulting in a tried-and-true I-beam shape that is able to provide the necessary resistance to both stress and deflection. The overall weight of the structure was drastically reduced when aerated concrete was chosen for the body panels. At up to 5 times lighter than its regular counterpart, these panels are light enough to float on water. They're also seen as a very sustainable building product, and have been being used in the building industry as such for over 70 years. They are always manufactured as precast blocks, because they require curing in a high temperature oven at roughly 8 times atmospheric pressure. This process is energy intensive, but its impact is offset by the long expected service life and the fact that one of the main ingredients used to make it is fly ash, an otherwise wasted byproduct of a coal-fired power station. However, the panels themselves do have a tendency to experience brittle fracture under high tension stresses, which is why the steel frame has been designed specifically to take the load in such a way that none of the bottom corner panels will be subject to such loading conditions. The wall and ceiling panels have internal cavities cast into them for weight reduction. The floor panels, though, are different. They are the most innovative components of the whole setup, differing enormously in both complexity and purpose. For starters, they have cylindrical aluminium extrusions cast into their body structure that act as channels for power cables, connecting the array of LED lights sunken into their top face. Aluminium was the ideal choice for this task, because it won't melt or deform during the oven curing stage. External aluminium cladding is also necessary to provide extra protection against chipping, especially during transport. Mounted into the top faces will be 24 LED light units, made of cast aluminium and thermoformed acrylic. Each of these lights will have a direct electrical connection to a control unit at the end of the panel, allowing each light to be programmed within the context of the wider network of lights, being controlled by Bluetooth using an app on the touchscreen. To secure direct electrical connections from the panels to the power hub, copper pins can be found in the ends of each panel that connect them to their nearest neighbour. The power hub is where all of the electrical components are connected, including all the lighting and recycling equipment. Due to the large power draws from the larger equipment, a 400-volt 3-phase power connection is required, which comes standard in any large commercial building in Australia, as they generally have higher voltage needs. This includes exhibition venues and large shopping centres that would host the system. Earlier I mentioned that Australia's recycling industry is in need of an update, and I'm not alone in thinking that. The Australian government submits a national waste report every year, and in it they mention their support for new recycling schemes as well as plans to increase the amount of plastic recycled in Australia overall. Currently, there's only one commercially viable operation in Australia participating in the chemical recycling of plastics, although they're undertaking a different goal. They turn plastics into fuel. What this project proposes is turning plastic into plastic, reducing the wastage that happens whenever a piece of plastic goes into landfill unnecessarily. It's already being done in Canada, France, England and the US, but here the market is still wide open. It won't all of a sudden replace the infrastructure here in Australia, but it can supplement it. I've estimated that the first unit, inclusive of all the manufacturing costs, the OEM equipment and even the 40-foot container to haul it all, will cost $165,000. Then a further $57,000 to pay a staff of 4 to transport it between 25 locations throughout the course of its first year. This will be covered by a $250,000 innovation grant put forward by Recycling Victoria. Looking beyond, the unit itself is the seed for a much larger company with huge goals. The recycled monomer output from this pilot plant during its travels will all be sold back into industry to support its ongoing maintenance costs, although local funding from around the country will also be acquired during these travels, gaining the capital to set up larger stationary operations that have the ability to recycle much larger quantities. As a not-for-profit, the money made from each stage of this growth will be funneled back into creating more operations, both mobile and stationary, eventually leading to a decentralised network of locally run chemical recycling plants, all overseen by a head office here in Melbourne. As well as a marketing tool for the company to increase awareness and raise funding, this first unit will also be an educational exhibition, a place for the general public to learn about what chemical recycling is and why it's such an important step on the road to creating a circular economy. The content it presents will be curated in a way that makes the technical information more accessible and interesting, although the space has also been designed specifically with user engagement in mind. The height and angle of the screen, for example, has been carefully chosen to accommodate the widest range of users possible, considering both children and adults, as well as those with movement aids like wheelchairs and walking sticks. The two display cases either side of the screen are built to display 4 samples each. The samples will include plastic at various stages of the recycling process to help people visualize what's happening. When the buttons at the top are pressed, the lights on the floor will trace a path to the recycling equipment which that sample is associated with, drawing a direct connection in the user's mind to how it all fits together. To keep the system safe after hours, a custom aluminium cage door is lifted into place and locked on the sides. In summary, Saber is both an engaging educational tool and a golden opportunity for the next big leap for Australia's recycling industry.